Have you ever taken one of those survival exams where you're presented with a list of all kinds of equipment, like, sleeping bag, lighter, food, water, matches, magnifying glass, and so on, and then they say, okay, you're stranded in the desert. What 5 things do you most want to survive in the desert? I usually do very poorly on those exams. However, if there was such an exam for a network technician and they said, okay, here's 50 different technologies, choose the 5 that are most relevant to your job, that essentially you need to survive in networking, I would say VLANs, and can I be bold in saying this? VLANs would make number 2 on my list. Seriously, right after the IP protocol, number 1. You got to know it. VLANs are right there because they are so pervasive in the network world. They are literally everywhere, from wireless segmentation to separating servers from guest network, from typical employees to the service provider environment, separating customers from each other. I mean, VLANs are everywhere. They saturate the network world. So in this nugget, I'm not only going to give you the core VLAN concepts and show you what VLANs are, but I really want to go practical on you, because that's one of the things I found is I can explain VLANs all day and people are like, oh, I see that. You'll see in a moment what I mean when I say I see the colors, that makes sense. But until you actually see some practical examples, especially how they relate to a service provider environment, sometimes it can be a little bit vague. Here are your do I know this already questions, so if you already know all the concepts, feel free to move right along. Before we can get into how VLANs work, we need to have a base understanding of how normal switching works. First off, normal switching, major improvement from the hub days, right? A hub being a device where everybody sees everybody. So when this guy wants to speak to this guy over here on the hub, everybody sees that communication, these spying eyes in the middle with Wireshark open. So a normal switch offers some separation because it has multiple collision domains. So if host A wants to communicate to host C over here, they can do that without bothering host B in the middle. That's good. However, a switch breaks down, if we can use it in that sense, when we look at the broadcast domain. In plain English, a broadcast domain defines how far a broadcast goes before it's stopped. A switch, and connected to another switch and another switch and another switch, will always have one broadcast domain. That is, when one of these devices send a broadcast, whether it be for a DHCP request, whether it's trying to look around for other services that are available, I mean, broadcast can be all kinds of things. Essentially, that switch receives it and sends it out all ports, including the uplink, when they send it out all ports, and they send it out all ports. It's one of the biggest constraining factors in our networks today to say, well, the more devices we have, the more broadcasts we have saturating our networks, and eventually you reach a point where just by plugging in a network cable, you can slow a device down because it's processing all these broadcasts, not to mention the saturation it does for a network and security ramifications, because everybody can, quote unquote, reach everybody. All you have to have is somebody with malicious intent, or sometimes even not so malicious intent, they just don't know what they're doing, running an IP scan, and you're able to see everybody else on the same subnet as you. So that's one of the key facts. A normal switch operates in a single subnet mode, meaning when I connect switches together, all these switches and devices attached will all be the same subnet. So we'll just say this is 192.168.1.0/24. All the devices plugged in will start with 192.168.1 because they're all part of the same network. This also represents one failure domain, meaning if you end up with a loop in the network, and loop is a bad call. Let's say a rogue DHCP server, right? This is something that takes down networks all the time, where you have a DHCP server that wasn't intended, handing out IP addresses from 172.16.1. Well, you're on this subnet, it's handing out the wrong addresses. You have computers dropping off the network like flies as they get these addresses from the wrong DHCP scope. That's what I mean when I say one failure domain. Essentially, you have one piece of fabric that extends through the entire network. And I've already mentioned this provides big security ramifications because people can see each other. Now, I wasn't planning to get practical on the slide, but since I added this to the bottom, I have to for just a moment. VLANs allow you to very easily configure quality of service, meaning I can create a subnet, a VLAN of devices, we'll just call, let's just say the blue ones, and I can then go to a device further down the road. Let's say it's a router that's connected to a WAN link where the bandwidth is limited. I can go in there and say, well, at all times, all cases, the blue VLAN gets the priority over the red VLAN, right? And it's very easy to do that. Whereas if you did not have VLANs, it's very difficult to identify devices from each other because they're all part of the same mush. So now as I describe VLANs, I'm going to start off with the foundations. Keep in mind, I'm not going to really talk practical at this point. I'm just talking about how it functions. VLANs logically group users. How does it do that? Well, what you do is you go in and create a VLAN. In this example, I'll say that we have a red and a blue VLAN. That I have represented here. Now, in the world of VLANs, you always use a VLAN number. The name is optional, but you have to have the number. So, maybe blue equals VLAN 2 and red equals VLAN 3, right? So we'll draw those lines over. So in this case, I go into the switch and manually configure the ports as to which VLAN they belong in. Now, this is me and you. As a administrator, go into the switch and we say, okay, port fast Ethernet 0/1 is in VLAN 2, the blue VLAN. Fast Ethernet 0/2 is in the blue VLAN. So we manually assign each one of those ports to that. This fast Ethernet 0/3 is in VLAN 3, the red VLAN, and so on and so forth. So I keep assigning these. Now, what I've done when I assign these things in the VLAN, if I could mentally have you envision a switch with a bunch of ports like this, if I say, okay, these two are blue and these two are red, it would be as if I did a ninja karate chop, yeah, snap, and broke that switch over my knee, and I now have two separate switches, one for the red VLAN and one for the blue VLAN. And that would completely separate them from each other, right? And their functional devices. And the same kind of thing here. So when this guy sends a broadcast, let's just say it's an ARP message, another type of broadcast. I want to know who is, 10.1.1.1. That's a typical ARP message. That would come out, all the blue ports, travel down here, all these blue ports, and yes, it does transcend switches, so it flows all the way down, and then out broken switch, non-Cisco. We've got another blue port down here where it gets the broadcast, right? So it completely segments the broadcast domains to where now our switches have multiple broadcast domains. Now, one other key fact before I add another twist to this, subnet correlation. When I first learned VLANs, I remember seeing something on Cisco's website. I can't find it. I looked. Where they had written down, they said VLAN equals a broadcast domain equals a subnet. Right? They made that correlation, and I scratched my head for a long time going, what does that mean? It means they're all really the same thing with different names applied to them. When I create the red VLAN, I create another broadcast domain. So all the red broadcasts stay in the red broadcast, right? I create another subnet to where if the blue VLAN used to be, 10.1.1.0/24, then the red VLAN has to be something else. It can't be 10.1.1.0. It'd be 10.1.2.0/24, right? So I'm trying to think which nugget of wisdom to add at this point. Okay, so let me go here. What if the red VLAN wants to get to the blue VLAN? Like this guy wants to talk to this guy. Can we do it? No. I know some of you are like, but wait, I thought you... No. Looking at this picture right here, which I will say is represented by a whole bunch of, here's the key fact, layer 2, meaning normal, mere mortal switches, right? These are normal switches. You do not have what's known as routing between the VLANs. The red cannot get to the blue, and the blue cannot get to the red. You have, in a way, completely segmented them from each other, which is phenomenal for access control. Not so good if you want that kind of communication, but it's possible. And the beauty is you can then filter it. I can say, well, the red VLAN can access the blue VLAN, but whoa, just a second. Only on port 80. Right? Which means it can only do web surfing or something like that over to the other side, HTTP, or only, you just see what I mean, right? Or only to this one guy at 10.1.1.50. No one else is allowed. Okay, so another key fact. Let me wipe this clean for a second. I mentioned that if the blue VLAN sends a broadcast, it comes out all the blue ports, and if the red VLAN sends a broadcast, it comes out all the red ports, right? Okay. What VLAN is that a member of? I know. Hang on. What? Okay. Yes, sir in the back. No, I'm sorry. I'm just kidding. Yes, all of them, right? Or, I mean, if you said both of them, all of them, you are absolutely right because those are known in the Cisco land as trunk ports. Okay, super MVP concept right here. When a packet comes into the switch, let's just say we've got this blue guy that sends a ping, right, to, Well, let's just do an ARP message. A lot easier, right? A broadcast. So it's not directed to anyone. It's a broadcast comes in. The switch takes that. Here's the packet, right, with all of its header information. Blah blah blah. I'm a broadcast. I'm an ARP message, and it takes its blue pen and says, "This guy is blue," right? This is known as a tag. Now, a switch is the only thing. Well, and I'll say there's exception to this rule, but the only thing that really understands tags. Like if this computer received a packet, if this actually made it down to here, and it left that little blue header on the front, this guy would think this is a bad packet. He'd say, "Whoa, hey, what's this junk in the header? It must be a bad packet. I'm going to discard it." So a tag is never allowed to reach the end devices. So for instance, when this guy sends an ARP, let's imagine we had a whole bunch of blue computers right there. The switch colors it, but before it goes out any port that connects to an end computer, it will actually remove that tag. If I could exit out, remove that tag from it. So this guy just sees an ARP. Here, can I give you a key fact? Computers never know what VLAN they're on. It's true. All they know is I have an IP address. I'm just communicating. It's a happy day in computer paradise. They never know which VLAN they're actually on. VLANs is a switch concept. It's a network superstar concept. It's nothing to do with the computers itself. Same thing with the red one. When it sends a ARP message, it's going to get the little red color or tag on the front of it, which is never sent to an end computer. But when it goes across these special ports known as trunk ports, it keeps them on. Meaning, as this ARP message comes to this one, it's configured as a trunk port, and the switch goes, "Oh, okay, I'll keep that tag on there." So when it gets down to switch 2 right here, switch 2 goes, "Oh, okay, looking at the tag, I see exactly what you're talking about. I'm going to send it to this guy because he's part of the red VLAN. I saw that VLAN 3 tag on there, so I'll send that." But of course, before it sends it out here, it does what with it? Removes it, right? Yanks the tag off there. Then it sends it down here, but keeps the tag on when it sends it out to this one. Any trunk port, it keeps the tag on there. Now, I will say there's very few things where I admit that other vendors do it better. I think this is one of them. Trunk is a Cisco term. You very rarely hear trunk in the industry outside of dealing with Cisco switches. Everybody else in the industry calls them tagged ports. And when you hear my description, it's like, oh, that makes sense. The name totally matches, where a trunk, it needs an explanation. Now, I would think the reason that we could have a different term is that Cisco does their trunks very uniquely. Meaning, when you configure a trunk port on most Cisco devices, it includes all VLANs by default. Meaning, if I add a green VLAN and a purple VLAN and whatever VLANs, they automatically pass down the trunk port because it automatically adds all VLANs. You can change that and you can limit what VLANs are allowed out a specific trunk, but by default it sends them all. Whereas other vendors, you actually have to go in and configure this port to say, okay, I'm going to add the blue VLAN. VLAN 2 is now allowed on that port as a tagged VLAN. Right? These ports, come on, can anyone tell me in the other vendors' world what they call them? Untagged. You got it, meaning it yanks the tag off the packet. Okay, so that's how the VLANs work and how switches really segment these devices from each other. Well, let's go practical on the VLANs for a moment. Here's some examples where you might see these used. Let's say you've got a larger organization or maybe a college campus, right? And you've segmented your network with Wi-Fi to where you've got this employee network. We'll say those are the blue guys, and then we've got the red guys, which represent the guest network. Well, someone has a laptop, and I know these are showing cabled connections, but they very well could be wireless signals going to all these different devices. You have somebody with a laptop on the guest network. Well, as they walk from building to building to building, they can stay on that guest network because you can stretch that VLAN all the way across the campus. So you don't have to create different segmentation standards and different networks for them as they cross from building to building to building, right? Maybe, for instance, I have an IP phone sitting on here. Maybe you want to start segmenting the different kinds of devices that are on your network. You've got the PCs, which are your normal user environments, segmented from the servers, and that's a really good practice because if you put, the old strategy, remember the old strategy? If you think back to yesteryear with networking, it was always put the server closest to the clients. meaning put them on the same network so these guys can always access those devices. Well, nowadays it's always about segmentation. Segment those servers from the clients. Why? Because if it's connected to the same network and you have a malicious user right here, you can go online and download all kinds of free tools to unleash some brutal attacks on that servers with no filtering whatsoever because he's in the same network. And a normal switch, under normal circumstances, cannot filter traffic going to the different devices unless you use VLANs. So that's why we segment our servers from everything else. Same thing with IP phones. IP phones are awesome in the flexibility they provide you, in how unified they can make your network and the communication that happens. However, they're also very hackable. Meaning, just about every IP phone runs a web interface where you can get in and manage the device, configure the device. And if you know what you're doing and you bust out a tool like Wireshark and you have access to those IP phones, like they are sitting on the same network as you, right, without VLANs, you can actually capture the traffic and convert it to a WAV file. So you can actually, remember in the old days where people were like, cutting into the lines with alligator clips and clipping on these butt sets is what they were called to hear what was going on. Well, in this world, you could just sit at your own desk and kind of tap into other people's conversations. Again, if you're good and you know what you're doing without some kind of segmentation. Huge use of VLANs right there. Last one that I have is this is used all the time. Anyone that's dealt with VMware, or Hyper-V, I'll just put HV, knows that you can take a server and actually split it into different identities and run multiple servers on there. Well, servers nowadays support tagging. This is where I kind of bit my tongue in the previous slide when I said computers have no idea what a tag really means, because normal computers don't. However, if you're using VMware, if you're using Hyper-V, you can actually create multiple server identities on here. And I can have, this is my accounting server, and it will automatically tag the traffic on VLAN 10, we'll say. So it's segmented from everything else in its own little accounting VLAN, whereas the other two servers I have running in here maybe just go in VLAN 1. That's the default VLAN. But that's why, by the way, every Cisco switch, when you pull it out of the box, is doing VLANs. Make no doubt about it. They are doing VLANs. It's just all ports are a member of VLAN 1, which is why everything can communicate. Now let me hit one final practical example that hits directly at the heart of this series, and that is VLANs and the service provider. Service providers are really becoming far more integrated and participatory with customers. Meaning, previously in the old days, you would have something like a frame relay network where customers would connect and they would say, "Hey, I need a link from Arizona over to Michigan," and the service provider would say, "Okay, let me build you a permanent virtual circuit, and here's your Delcy numbers to identify that connection." It's kind of like a MAC address, if you will, for that. And then these guys would tag their traffic with specific Delcies that the service provider would see and say, "Oh, okay, well, let me transport you to Michigan," and so on and so forth. Well, those days are going away rather quickly, I might add, because it requires service provider involvement every single time the customer wants to do something a little bit different, and it can get a little bit costly when you start adding a bunch of links between a bunch of sites. So what service providers are doing more and more and more is going with designs like, for instance, Metro Ethernet, which on their underlying foundations use MPLS, essentially another way of tagging. Just think of it like the big brother, or I guess it'd be the little brother. Frame relay was first, right? So it's the little brother, the few generations beyond from frame relay method of tagging your traffic, to where essentially you can hide what the customer is doing from what the service provider does. So essentially, let me just give you a good practical example here. We've got Tonka. Like I have kids at home and they have Tonka trucks. I don't know what parent company that is, so I'm assuming Tonka. So let's say they have a Phoenix manufacturing plant. They're cranking out these little toy trucks, and they have the what is it? Oh, San Diego. I was thinking, what was I thinking? San Diego office, right? Which is the corporate headquarters, and they want to have these things linked. Well, with MPLS and Metro Ethernet, a lot of times you can terminate to where you're actually plugging into an Ethernet connection. That's the Metro Ethernet field. You've got fiber optic or some kind of cable coming in here that terminates on Ethernet, to where you can literally bridge these two networks together as if you had one big old Ethernet cable going between the two, right? This is awesome. in terms of the flexibility and design constraints that it allows Tonka to have when setting up their network. So let's say they had a voice over IP network on VLAN 10, right? And they have the voice over IP server over here on VLAN 10, and they want to do, maybe they've got other VLANs, VLAN 11, VLAN 12, VLAN 13, all these different VLANs that they actually want to bridge across, on a trunk port. Now, can I first off mention that if I were recording this series 8 years ago, maybe I don't know, it's not that long ago, this would be like a dream. People are like, yeah, no. VLANs stop when you get to the service provider. Well, the dream has arrived to where they can now connect those layer 2 networks through the service router over, for example, a Metro Ethernet connection. But here's the problem, right? We've got Tonka making their trucks and doing their thing with their little VLAN 10. And I've got Milano. Where do I come up with these companies? I ate a cookie this morning with my coffee by Milano. So Milano's creating cookies in Dallas and Eugene, and they actually have a server and some clients on VLAN 10. So, whoa, wait a sec. How is Milano cookies using VLAN 10 into the same cloud? Because it really is. It's the same carrier, same service provider, same VLAN 10 that's coming in there, and it's not ending up sitting there in Tonka's LAN. Well, that's where service providers use this concept of Q and Q. What's up with that name? Well, the actual tagging standard when you connect two switches together on that trunk port, right, is 802.1Q. But it's such a common standard, most people don't say, well, that's an 802.1Q trunk. Although I guess a lot of people do say that. But a lot of people just say .1Q, or Q. Q is the tag that is added to that label. That's the standard. That's what allows a Cisco switch to connect to vendor X, the heathen brand of switch over here. And they still understand each other in terms of VLAN languages, is because they both are tagging using the same thing. So maybe some of you are putting the puzzle pieces together. What is Q and Q? Well, it is a 802.1Q tag inside of another. Now, hang on. If you're learning VLANs for the first time, let me just say you're jumping off the diving board with this one. I mean, I know when I first learned VLANs, I was like, whoa, hang on, let me think through this. This is taking it to a whole new level really quick. So you might just want to pause, breathe, go back to the VLANs, make sure you got that down. Then here we go. What happens is when this guy sends a packet on VLAN 10, let's just say this is configured as that trunk port, what's going to happen is it's going to say, okay, I'm going to put that VLAN 10, we'll just say it's the red VLAN tag on the front of it. Now, what kind of tag? It's an 802.1Q tag, right? So it comes in here into the service provider, who actually wraps the entire thing in an outer tag. In this case, they being the service provider, you and I, have defined that customer, Tonka as a whole, as VLAN 55. And that is what allows us to separate and hide the Tonka VLAN information from all the other customers that we have. And we know they're all going to be using VLAN 10 because it's a low VLAN number. It's very common for somebody to use something like that. So we can actually wrap the Q tag inside of another Q tag. You get where this is going, right? Q and Q, or the official standard is 802.1AD. So we, as a carrier, can start defining one VLAN that represents perhaps hundreds of sites that are connected into in this case, we'll just say a Metro Ethernet environment that allows the customer to tag whatever VLANs they want, but we, nor our other customers, ever see them. Now, there are many other ways that service providers use VLANs, but that's a lot of times, the one you just saw, is a very customer-facing one that you will know well as you start dealing with, for instance, Metro Ethernet technology. And by the way, just to fill in one more gap, that is often known as a .1Q tunnel. That's actually the configuration that you'll do. We'll do that a little bit later in the series on setting up that point-to-point connection, right? So it really gives you that visual, like there's this tunnel. Here's us, the service provider and network, right? And our customer is sending that VLAN 10 traffic, which enters the tunnel, which we tag as VLAN 55. And as it leaves to go to their whatever customer site there is, it retains its VLAN 10 tag coming out the other side. That's that configuration. So we have seen the core VLAN concepts. Man, I'm telling you, when you get into the service provider world, everything moves faster. I've never taken somebody from zero to Q and Q tunneling in the same nugget, but we've done it now. Core VLAN concepts into many practical examples of it until finally seeing how we would use it in a service provider environment. I hope this has been informative for you, and I'd like to thank you for viewing.